Hello everyone, myself Jyoti Mahekar, and today we are going to study about the classical theory of Raman effect. In the last lecture we studied about the quantum theory. So why do we need quantum theory and why do we need classical theory for Raman effect? So when we discussed quantum theory, basically quantum theory is required for predicting selection rules and predicting intensity rules. But when we talk about classical theory of Raman effect, this classical theory is required to explain basic concept of Raman effect, that is what is polarizability. So using classical theory, we explain polarizability of the molecule. So classical theory, it is as important as quantum theory of Raman effect. And so let us first try to understand what is polarizability of the molecule, or when we can say that the molecule is polarized. So suppose we apply a static electric field on a molecule. It produces separation of center of positive charge and negative charge. When I say positive charge, I mean to say nuclei. And when I say negative charge, I mean to say electron. So when a static electric field E is applied, it produces separation of the centers of nuclei and the electrons. Now, because of this separation, there is an induced electric dipole moment mu of the molecule, and then we said that the molecule is polarized. In the earlier lecture of electron spin and all, we have discussed about magnetic dipole moment, which is mu. So magnetic dipole moment mu, it is because of the application of magnetic field. Here we are dealing with uh, electric dipole moment, which is because of the application of static electric field E. Now this dipole moment mu, it depends on the field E. When you apply electric field, then only there is a electric dipole moment. It is proportional to electric field. So mu is directly proportional to E. If you will increase the value of applied field, then the value of electric dipole moment mu will also increase. So I can say mu is equals to alpha E. Mu is proportional to E, and when I remove that constant of proportion, proportional sign, I will get constant of proportionality, which is mu is equals to alpha E. So, or I can write as alpha is equals to mu upon E. So this alpha, it is called as polarizability of the molecule. And how can we define this polarizability of the molecule? It can be defined as mu, ratio of mu to E. What is mu? Mu, it is the dipole moment induced by the field, and when I divide it by E, that will become per unit field. So polarizability of a molecule, it is defined as dipole moment induced by the field per unit field, and we can write alpha is equals to mu upon E. Now if we apply the same field in different directions, mu, and hence the polarizability, it will not remain same, it will change. And in that case, we can call the polarizability to be anisotropic. When the electric field E is applied in different directions, polarizability does not remain same. It changes with the direction, and that is called as polarizability is anisotropic in nature. It depends on orientation of the molecule related to the applied field and the separation of atoms in the molecule. So when we are talking about the orientation of the molecule will change depending upon its rotation. If the molecule is continuously rotating, its relative orientation will be different. So in a way, we can say that polarizability, it depends upon rotation. And when we are saying that polarizability depends on the separation of atoms in the molecule, we know that when we consider a molecule, we have atoms in the molecule which are continuously vibrating about their main position. So the vibration and rotation has an effect on the polarizability of the molecule. So in case of diatomic molecules, even our common sense tells us that it is easier to stretch the molecule along internuclear axis. It will be easy. as compared to the other directions. So we can show that the dipole moment, electric dipole moment along internuclear axis, it is twice as compared to the that induced along the perpendicular axis. So when you plot it, it gives you an ellipsoid, and that is called as polarizability ellipsoid. So the mu in other directions gradually decrease. Along the internuclear axis, it is maximum. Then it gradually decreases along the perpendicular axis again that way. So if you plot, it gives you a ellipsoid. So you can draw a polarizability ellipsoid so as to represent the direction of polarizability. And see, this is the polarizability ellipsoid. Now, if you take the cross section of the polarizability ellipsoid, you will get circular. Why? Because polarizability of a diatomic molecule is the same for all directions at the right angles to the bond axis. And that is how the polarizability ellipsoid has a circular cross section in this direction. So you can see that the polarizability ellipsoid, it is having this shape, but if you take the cross section of polarizability ellipsoid, it is a circular cross section. Now this polarizability ellipsoid has the same shape for all diatomic linear polar atomic molecules, differing only in the sizes of semi-major and semi-minor axes. And now instead of a static electric field, up till now what we were applying was static electric field. Now instead of static electric field, suppose we apply oscillating electric field, then let us see what happens. So now instead of static field E, let a radiation of frequency nu be incident on a sample of diatomic molecules. An electromagnetic wave has an oscillating electric field, and the frequency of oscillation, suppose it is nu. So in this case, we can represent the oscillating field as E is equals to E0 sine 2 pi nu t. This E, it is representing the oscillating field which changes with the change in frequency. Now we know that mu, it is given by mu is equals to alpha E, and if I substitute the value of E as E0 sine 2 pi nu t, then I will get this expression: mu is equals to alpha E sine 2 pi nu t. That means when my field is oscillatory in nature, that time my dipole moment is also oscillatory in nature. तो यहाँ पे आप देख सकते हो कि mu, it is oscillatory in nature. So according to classical electrodynamics, an oscillating dipole emits radiations of its own frequency. So hence a radiation of frequency nu, same as the incident radiation, is emitted here, and this is what is called as elastic scattering, or it is called as Rayleigh scattering. So when we studied the Raman effect, that time we studied that the scattered radiation, it consists of three components. One component which is having frequency same as that of the incident radiation, and other two, they have either frequency higher than that of the incident radiation or lower than that of the incident radiation. So the one which is not modified, or which is unmodified, or which is unperturbed, or which is unmodified in the Raman spectrum, that is what is because of Rayleigh scattering. And here we can see that an electric dipole that is oscillatory in nature, and according to classical electrodynamics, it is emitting frequency of its own frequency, emitting radiation of its own frequency, and that is what is reason for getting a parent line in the Raman spectrum. Now, if in addition to the above, there are some internal motions in a molecule which can change polarizability periodically, then the oscillating dipole will have superimposed upon it the effect of these motions also. So when we refer to internal motions, basically we are talking about vibrational motion and rotational motion. Vibrational motion and rotational motion of a molecule, they are referred to as the internal motions of the molecule. So these internal motions could be rotational or vibrational, and they also have a role to play in the polarizability of the molecule. So what is the effect of rotation on the polarizability? What is the effect of uh, vibrational motion on the polarizability? or in a way we can say that what is the effect of internal motions on the polarizability of the molecule, that we will study in the next lecture. Thank you so much.